So this file is the Chapter 9 practice questions, and I really encourage you to open that file and follow along and make sure you can get all the answers with me. So the first several questions, well, all but the last actually, are going to be coming from this data comparing the number of counselors and librarians, the pay of counselors versus librarians in public schools for the last 12 years. So our first thing to do is going to be construct a scatter plot of the data and see if they look like they have a positive, negative, or no correlation. So let's get this in Excel and get started. So to get a scatter plot, you're going to want to click and hold to select all of the data in Excel. Then you'll go to the Insert tab, and in our chart sections in the middle, we're looking for a scatter chart, which should be this last one. So if you click on that, we just want a regular scatter plot of just the dots. So we put it that way. And then to make sure that it did plot things the way we thought it should, it'd be a good idea to go and click on one. So here's this data point. It tells me that it is the point 48.2 and 46.7, which is my first data point up here, and it is showing indeed. So we might want to change this to be like public school pay, something along those lines. And then when you click on it, you get this little thing that lets you add. So we're going to add AXI titles so that we can label here, the counselors, and then over here the librarians. If I could spell them. Okay, wow, that was rough. All right, and so you can leave scatter plots like this, but since nothing is below 40 in either direction, I'm going to adjust. So if you right click and you go to Format Axis, in this menu on the right, it'll pull up the minimum and maximum. So I'm going to change my minimum to 40. And then when you click out of that, it'll readjust. And now I've got an even better picture, and I see I could actually change that to 45. Okay. And now we can see what's going on better. Then we'll want to click over on this one, and if you still left your format axes up, you notice when I click from here to there, those numbers in the right change to reflect my other axis. And so we'll change this one to start at 45 as well. And now we've got all of our points, all 12 of them, and we can see what's going on with them better. So you didn't have to do the rescaling, but it does help. Right? I encourage you to keep the scale roughly the same on the two when possible, just so that there's not any skew of your slope. Okay, when looking at these, you can see that as the pay for a counselor rises, so does the librarian pay. In fact, if your eye were to draw an imaginary line here, you would see a line that has a positive slope. So these appear to have a positive linear correlation, and a fairly strong one at that. So we found that this had a strong positive linear correlation. And we know that it was positive, so the strong we'll find out for sure in a moment. But the positive is because when counselor pay went up, so did librarian pay. So they move in the same direction, meaning they have a positive linear correlation. Our next thing is to go back in Excel and calculate the correlation coefficient and interpret the results. So because we found a positive image in our scatter plot, we're going to expect to find a positive R, And I also think it's going to be a pretty strong R, meaning it's going to be pretty close to +1. Let's see. So going back to our Excel file, we want to find the correlation between the two. So that function is equal correl, C-O-R-R-E-L. And then the formula tells you array 1, comma, array 2. So we're going to click and hold to select all of them, and then put a comma, and then click and hold to select all of them. Now, if you don't have the same number of elements in your first and second parts, it'll give you an error. So make sure you've selected everything. You also could have typed in those cell references. I usually find it easier to click if you can see them, just to make sure you've got the correct one selected. And then we're going to push enter, and it gives us a correlation. So we predicted it would be positive since we saw a positive correlation happening in our scatter plot. Indeed, it is a positive number. And we also thought it'd be fairly strong, meaning pretty close to 1. And 0.9948 is very close to 1. So it is near perfect, not quite, so it's technically just strong linear correlation. Now, if you did want to find the correlation and you did them in the wrong order, meaning you started with the y's and then you chose the x's, you should find that you get the exact same number. Right? So it doesn't matter the order for correlation, it just matters the sets of data pairs. Our next goal is to use a hypothesis test to prove that there really is a correlation in the population and not just in our sample of 12 years. So first we need to make sure we understand what our null and alternative hypotheses are. Our null is that our population correlation is 0, meaning there is no correlation in the population. We know there's a correlation in the sample, but the point of our sample is to say things about the population. So the alternative is that it's not 0, meaning there is a correlation in the population based on our sample results. And so there's lots of different ways to do this. We're going to take the simpler way out and use what's called the Pearson test for the correlation coefficient. So you'll find the table I have here goes much longer than just to an n of 13. In the appendix of your book on page A26, there's 2 different tables. Make sure you get table 11 with the Pearson correlation coefficient. And so we need to first know what our n is. The n is the number of pairs of data. So if you go back and look at the data, you'll see that there are 12 rows with numbers. So in our instance, n is 12, right here. And then it tells us to use an alpha of 0.01, right there. So we see where these two come, and it gives us this number 0.708. And in case you're not sure what to do with this, it has a little direction at the top of the table. It says the correlation is significant when the absolute value of R is greater than the table. So RR was 0.9948, technically 12, but that's enough decimals. Right? This table only goes to 3 anyways. And so the absolute value of R is still 0.9948 because it started out that way. And our critical value here is 0.706. Nope, sorry, 8. 0.708. Our R is definitely greater than that. And since it's greater, that means we can reject our null, meaning that there is a correlation in the population. Right, we haven't proved that it's a positive correlation, we've just proved that there is one, right? Because this one is regardless of the sign. So you just look at your correlation, and as long as it's bigger than whatever value you get from this table, then you can say that the correlation continues to the population and not just your sample. Now that we've got our scatter plot, we want to find the regression equation. So you go to one of your data points and you right click, and then you want to go to add trend line. You also could have gone over here to the plus sign and down to trend line as well. If so, make sure that you tell it you want a linear one. It's also not going to pop up the menu on the right, so I'm going to do it my normal way of right clicking and adding a trend line. It pulls up this menu on the right where it gives you all your options. We want linear trend lines. And then I want it to display my equation on the chart, and I'm also going to have it display the r-squared. We don't need it for this question, but we will in the future. So you see this little box appears that gives you a y equals, and that is going to be our regression equation. So where x here is the counselor pay, you can plug in and find out a predicted librarian pay. Now we want to use the regression equation we just found and try and predict the salary of a librarian if the counselors have a salary of $59,500. So our equation that we got, just copying it exactly as it's written in Excel, was this. But to make a little more sense out of it, I'm going to write librarian, abbreviated, is this. So we can keep straight what to plug in where. Now, one other thing to remember is we're not plugging in 59,500. The way it was written was 59.5, right? It was written in thousands of dollars. So that's the number we're going to plug in. So 1.0713 times 59.5, and then we'll subtract 5.05. When you do this in a calculator, you should get 58.692 and then a couple of other numbers. So if we wanted to write out what we would predict a librarian average salary would be, librarian average salary is going to be 58,692. That would be our prediction, using what we know from the last 12 years of the relationship between the average librarian salary and the average counselor salary. And one of the last things we want to do to interpret our regression equation we found is to find the coefficient of determination r-squared, which is literally just the r that you found back in the second problem squared. So you could take 0.994812 and square that number, and if you round to just a couple of decimal places, you'll get this number. That should look familiar because back when we were adding the regression equation, I also said to check that box below, and that was to get the coefficient of determination. Correlation coefficients, just regular R. Okay, so what is the coefficient of determination? Well, it tells us the percent of variation that's explained. So we take this number that we have, convert it to a percent, and we get 98.97. So that's what that means is 98.97% of the variation in the average pay of a librarian can be explained by the variation in the average pay of a counselor. So whatever it is that makes a counselor pay go up and down, it's a very similar factor that makes the librarian's pay go up and down. In fact, it explains 98.97% of the variation. So we call that the explained variation. The unexplained is just whatever's left. So we do 100% minus the 98.97% to get our unexplained variation, which is just 1.03. So that means just a little over 1% of the variation in average pay of a librarian is not explained by the variation in the average pay of a counselor. So it's a very good predictor, but it's not a perfect predictor. So some of the time you'll be off a little bit, and that's what this unexplained. So if you're ever asked to calculate the explained variation and the unexplained, this is what it's saying. The explained variation is just your r squared converted to a percent form, and then your unexplained variation is just the rest. And so that's the reason we look for high R's, high correlations, because the higher the correlation, the higher is going to be the coefficient of determination. And if that's high, that means we're able to use our X to explain a lot of what happens to our Y, and it makes our regression more useful and more meaningful. This last question does not use the information in the previous sections because it is a multiple regression. It tells us that here we have the relationship that gives us the sales, so that sales is Y, where X1 is the number of stores open at the end of the fiscal year, and X2 is the average square footage per store. And we want to predict sales depending on different values of the numbers of stores and the square footage per store. So to do that, we use our equation, and then you just plug in the values for X1 that it wants. Oops, that's not plus, that's minus. 8.413698. And so then you would be sure to multiply, and then you add and subtract, and you should get 2372.08. So that's, again, this is in millions. This is $2,372 million, or 2.3 billion if you want to translate it. And so you just do that for each of them, using the equation, plugging in the new values of X1 and X2, multiply, add, and subtract, and then you should get 2,286.97, so 2.2 billion whenever they have a couple less stores and each store is a little smaller, right? That's what happened in our X1s. And then in the next one, do the same thing. Oops. Forgot to change my number. That's 952 stores now, and a square footage on average of 3,601. So again, fewer stores and each store is a little smaller. And their average sale is 2,223.95. So 2.2 billion still, but lower than before. And again, adding in our new numbers, which is 914 stores, and each one with 3,594 square foot on average. And that comes to sales of 1.9 billion, or 1,933.98 million. So these are all in mils. It's good to remember the units it in case you need to convert it. All right, so for this question, we'd probably answer them just like that. If you were writing a paper, it would make a lot more sense to write that as 2.372 billion and 2.286 billion and so on, instead of having thousands of millions. So with all of these, it's just important to think as you're coming up with the numbers.